Today we're going to be talking about a book by Werner Heisenberg called Physics and Philosophy, The Revolution in Modern Science. And this is a book that I had bought over a year ago probably, but I had set it aside because I said I should read that when I know more physics. Otherwise I won't know what he's talking about. But this week I decided to just go for it. Actually last week rather. By the way, I had this episode ready to record and upload last week, and then I got what I think was bronchitis from my sister's family, which didn't hit me that hard, except that it knocked out my voice for like 6 days. So I was moving along very steadily on my work schedule, and then that happened. And there are a lot of things that you can do if you've lost your voice, but recording a podcast is not one of them. But anyway, so I read this book last week, and I was pleased to find that reading it did not really require any knowledge of physics. I'm sure that a physicist would get more out of his discussions, for example, of why he disagrees with this physicist about the interpretation of the data. But there was plenty in this book for the layman to enjoy. And the book is called Physics and Philosophy. What he's talking about is the connection between modern physics and the physics that had been developed over the course of the 20th century. And this book was published in 1962, which makes it by far the most recent book that we've looked at. And it's the kind of thing that's hardly canon yet, but it fits very comfortably along other older pieces of similar work. So you have Descartes, who was a mathematician, then reflecting on philosophy. And here, as we'll see, you have Heisenberg, who won the Nobel Prize for Physics, also reflecting on philosophy and what he thinks the implications for his work and the work of the people around him are for philosophy generally. And the physics that Heisenberg largely dealt with was the area that is now generally called quantum physics or quantum mechanics. And I in part wanted to read this book because, in my mind, quantum physics makes me think of two things. One is some impenetrably difficult math and physics stuff that it would take a long time to learn how to do. And so it's not really worth it for the layman to try to study it. You can either take the long road all the way through the necessary prerequisite math and all the prerequisite physics and whatever it would take to then try to understand quantum physics in a formal way. Or you better leave it alone and trust that the people who have gone through that process will hash it out and come to the best conclusion, and you can take their word for it. And that's, of course, a weak epistemology, because that's an appeal to authority. And there are all kinds of situations where we would never do that. But in certain situations, like when there's a very complex science to learn, we unfortunately don't really have a choice. Unless you want to take the time to learn it all yourself, and even then, just because you know enough to understand what the guys are talking about on a technical level, doesn't mean that you can interpret it better than them, better than somebody who's been working on this for 30 years, for example. Though interestingly, there is a pattern of young people, Heisenberg was one of them, coming into physics in particular, but other fields as well, and blowing it wide open with some new angle. But for me, quantum physics makes me think of two things, and that's the first one. The other one is the way that this spooky sounding word and some of the unanswered questions that it has left, even for the top experts in the world, is viewed by a certain class of snake oil salesmen as an opening into which they can try to slip to hawk their wares. A characteristic example of this is a documentary that I saw in probably 2008, which was called, I don't even really want to say the name of it because I don't want to promote this dumb thing, but I'm disparaging it, so I guess it's okay. It was called What the Bleep Do We Know? And I was a teenager at the time, and I was watching it with some of my college friends. And even then, we all thought it was pretty stupid. But because I didn't view that documentary as part of a larger trend or a type of information product, I didn't have the active hostility toward it that I think I would have now if I were to watch it again, which I never would. But people use the phrase quantum physics or quantum mechanics to justify or explain or imply the possibility of all kinds of things, just because, from what I understand, quantum mechanics is basically at the edge of what we understand in science now, of what is explained. And because you're at that frontier between the explained and the unexplained, some people view that as an opening for bad thinking, when what it really needs is a lot of very careful, good thinking by a lot of really smart people. So those are the two ways that I had thought about quantum physics before reading this book. But I was kind of thinking that neither of those are really enough. That if there is a section of cutting-edge science that deals with things that affect philosophy, then it won't do to just go on as if that didn't exist because it's too complicated for us. As non-experts, unless you're a physicist, in which case this applies to you also, but maybe from the other side, we have to try to take this field of knowledge, even a highly simplified version of it, a model of it, and put it somewhere in our understanding of the world. Even if that place is simply that there are these phenomena that no one yet has been able to explain. So we're just going to put a question mark on it and leave it there, but we're going to be aware that it's there. If what we are trying to do is understand ourselves and the world and our place in the world, then this siloing of thought into philosophy on one side and physics on the other and saying those two are separate doesn't make any sense. We have to be willing to roll our pants up to our knees and go wading into the shallows of these deep waters, even if it's a little uncomfortable because it's outside of the topics that we think about the most. Before looking at passages from Heisenberg's book, we can look at his life a little. He was born in 1901 in Würzburg, which at that time was in the Kingdom of Bavaria in the German Empire. It's today in roughly central Germany. And his father taught classical languages in a high school, and he later became Germany's only professor of medieval and modern Greek studies in the university system. And while Heisenberg was, of course, best known as a physicist, the fact that he wrote a book like this, and he was well versed in classical philosophy, seems that it was very likely, at least in part, his father's influence. When he was a late teenager, he went on a hiking trip in the Bavarian Alps, and on that trip, he was also reading Timaeus, which is a dialogue of Plato that involves reasoning about the possible nature of the physical world and of people. Heisenberg later said that, quote, "My mind was formed by studying philosophy, Plato, and that sort of thing." And also, "Modern physics has definitely decided in favor of Plato. In fact, the smallest units of matter are not physical objects in the ordinary sense. They are forms, ideas which can be expressed unambiguously only in mathematical language." End quote. And that's a little bit of a teaser of what he gets into later. And he does not at all tie himself into knots trying to connect modern physics to ancient philosophy. But he finds some interesting connections like that one. In 1919, so now he's about 18 years old, Heisenberg went to Munich as a member of the Freikorps to fight against the Bavarian Soviet Republic that had been established around that time. And he later said of those days that they were, quote, "playing cops and robbers and so on. It was nothing serious at all," end quote. And he said that his job was restricted to seizing bicycles or typewriters from red or communist administrative buildings. And maybe his role was relatively minor, but the Bavarian Socialist Republic or Soviet Republic is a very interesting episode in German history. It happened during this time around the end of World War I, where there was a lot of upheaval that you don't learn very much about in school. There was this entity or pair of entities that existed over a brief period. The first one was the People's State of Bavaria that existed from November of 1918 to February of 1919 until Kurt Eisner, who was at the head of it, was assassinated. And then there was the Bavarian Soviet Republic, or it's sometimes called the Bavarian Socialist Republic, which from what I can tell mostly existed in April of 1919. So this state existed on and off in a probably kind of informal way, but it would require more reading to see exactly what was going on there. And this is in the spring of 1919. So it's between the armistice, which is in November 1918, and the Treaty of Versailles, which is June 28, 1919, 5 years to the day after the assassination of Archduke Ferdinand. But so the fighting between countries has stopped. There's an armistice. And now there's an attempt by, it's complicated, but the first leader of this attempted breakaway state is Kurt Eisner, and he doesn't last very long. And then there's another guy, Ernst Toller, and he lasts like a week. And then there's another guy, Eugene Levin, and he lasts a couple weeks. And then it falls apart. And Eugene Levin, the third guy, apparently actually had a direct connection to Lenin. So that would be the reason why calling it a Soviet republic would be suitable, not just a socialist republic, is that there was, reportedly, this would require a little more research, a direct connection to Vladimir Lenin in the Soviet Union. But anyway, it sounds like Heisenberg was just at the edges of all that. He was a teenager running around in the streets, fighting against the Reds, presumably against these guys who were setting up the Soviet Republic there. But he was stealing bicycles and typewriters and stuff. Then he went to school, and I didn't get the impression from what I was reading that he was immediately recognized as an amazing prodigy. He was obviously very gifted, but he doesn't appear to have been a kind of runaway genius like somebody like Gauss. But at the same time, it was a relatively short route between the beginning of his formal education in this field and him releasing a very significant paper. And he had studied some of this stuff earlier, but it wasn't as if somebody had been training him from birth to be a physicist. But it might have in part been some of the teachers that he had. But let's look at the timeline and some of those teachers. From 1920 to 1923, he studied physics and mathematics at the Ludwig Maximilian University of Munich under Wilhelm Wien, who received the 1911 Nobel Prize in Physics, and Arnold Sommerfeld, who, along with his own discoveries and contributions, would be doctoral and postdoctoral supervisor to 7 Nobel Prize recipients. Then at the George August University of Göttingen, Heisenberg studied under Max Born, who received the 1954 Nobel Prize, James Franck, who received the 1925 Nobel Prize, and he studied mathematics with David Hilbert, who was a major mathematician from that era. And the Nobel Prize has questionable value in a lot of fields, but if it has value anywhere, it seems like it would have value in physics. That physics is a field where you can more readily determine who has made some kind of significant contribution. And Heisenberg was hanging out with a bunch of people who, if they didn't have a Nobel Prize at that time, they would get one later. So in 1923, he received his doctorate, which also reflects some differences in the education system. Now a doctorate is something that you would get not in 3 years, but in 7, though I think in Europe sometimes it's faster. But more importantly, it would be after you've gone to university and then done some kind of master's degree or something like that. And here he went straight to a doctorate, which I think maybe is just the name that they're giving for the degree that he got. Anyway, that's a detail. And here I want to read a section that's not from Physics and Philosophy, but the very nice edition of this book that I read from HarperCollins Publishers included some articles at the end that were also by Heisenberg, published in other places. And one of them was called The Decision to Study Physics, and it includes an anecdote of an early meeting, or maybe the first meeting, between Heisenberg and Arnold Sommerfeld. So this would have been not from when Heisenberg graduated, but more around 1920, a little bit earlier. And Heisenberg says that Sommerfeld said, quote, "If you want to study science at all, you must first make up your mind whether you want to concentrate on experimental or theoretical research. From what you have told me, I take it that you are much keener on theory. But didn't you do experiments and dabble with instruments at school? I said that I used to like building small engines, motors, and induction coils, but all in all, I had never really been at home in the world of instruments, and the care needed in making relatively unimportant measurements had struck me as being sheer drudgery. Still, even if you study theory, you will have to pay particular attention to what may appear trivial little tasks. Even those who deal with the larger issues with profound philosophical implications, for instance with Einstein's relativity theory or with Planck's quantum theory, have to tackle a great many petty problems. Only by solving these can they hope to get an overall picture of the new realms they have opened up. Even so, I'm much more interested in the underlying philosophical ideas than in the rest," I said rather bashfully. But Sommerfeld would have none of this. "You must remember what Schiller said about Kant and his interpreters. When kings go a-building, wagoners have more work. At first, none of us are anything but wagoners, but you will see that you too will get pleasure from performing minor tasks carefully and conscientiously and, let's hope, from achieving decent results." End quote. So that's a little exchange there between Sommerfeld and Heisenberg. And Sommerfeld asks him whether he wants to be in theory or in experimental science. And Heisenberg says, well, he doesn't want to do a bunch of little measurements and petty things like that. And Sommerfeld says, even in theory, you're going to have to answer little questions that might look petty. You have to answer those in order to get to the bigger questions. And obviously, we can't compare any field to physics, but I do think that that's a reasonable way to look at answering any kind of question that you want to be answering. It's that you have to break the bigger question into smaller questions, and then break those smaller questions into smaller questions as much as is necessary. And then starting at the bottom, answer all those little questions and work your way back up to that big question that you started with. And it's interesting to think about that kind of theoretical work as involving tasks similar to the physical preparation of whatever involved in experimentation. An example I'm thinking of is my sister worked at the NIH for a while, and she would talk about part of her work involved filling up lots of little beakers, I guess they were. I never saw her do this. I just heard her explain it, so I might be explaining it wrong. But they were like little plastic containers, and there would be a bunch of them in a tray, and they had to be prepared in a certain way. They needed a certain amount of this and then a drop of that and whatever. And it took a while to do this. And her husband, who did similar work, didn't really like that part of the job. But she liked it because she found it kind of meditative, that you have to do this physical thing for a while and you have to concentrate on it and you can't mess it up. But Sommerfeld was telling Heisenberg that theory involves that kind of work also. It just looks a little different. And another detail about Heisenberg's life up to that point is that he was a member and a scout leader of a German scouting organization comparable to the Boy Scouts, and he helped to organize a trip to Finland for that group in August of 1923. So that was something else that he was doing when he was a student, as he was going camping. But then in 1925, so 2 years after he graduated, 5 years after he started his formal study, when he was only 23 years old, he published a paper titled Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations. And this was a breakthrough paper in what is now called quantum mechanics. And along with Max Planck, Max Born, Paul Dirac, and some others, he is among the central developers of quantum theory. In 1927, so only 2 years later, he developed what's now called Heisenberg's uncertainty principle. And since I've encountered the uncertainty principle in a few different contexts and a few different books over a few years, and because it seems to have at least one important implication for epistemology, I've made some effort to try to understand it superficially. What people will say, and what I believe Heisenberg says in passing about it, is that it places fundamental limits on our ability to measure the position and momentum of a particle. And this isn't because we don't have the instrument to do it. It's that there's something fundamental about the universe that makes it so it's not possible to measure the exact position and momentum of a particle past a certain point. And if that's true, it's an important limit of knowledge. And I don't presume to understand this in any detail, but the equation for the uncertainty principle is surprisingly simple. And this kind of thing does not lend itself very easily to an audio format. But since it's quite short, I'm going to try to explain it, and hopefully I'll be able to give the general idea. The equation looks like this: uncertainty in position times uncertainty of momentum, and we just label those two things with variables. Change in x times change in p is always greater than or equal to Planck's constant over 4 pi. That's the whole thing. And what this is describing is not a law about how you're supposed to solve a certain kind of equation or something. It's describing the way the universe behaves. And Planck's constant is just a very, 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 very small number. Doesn't matter. It's a very small number. If you want, you can look up the Wikipedia page and read about it. It's the quanta of action, the smallest possible unit of action, which, by the way, that's what a quantum is. It's the smallest part of anything that is in an interaction with something else. But so the uncertainty principle states that the uncertainty in the position of a particle times the uncertainty in its momentum must always be greater than or equal to this very, very small value. Planck's constant is already small, and then you divide it by 4 pi. So it's a very small value. Now, the thing is, in daily life, we never come up against this problem. We're never dealing with anything that small. But in particle physics, you do deal with things that are that small. And so what happens when you get past that point? What happens when you start to get over a point where the uncertainty in the momentum and the position of a particle might be less than Planck's constant divided by 4 pi? Well, you can watch some YouTube videos that are very mysterious and interesting of a guy with a laser thing trying to demonstrate this. And what happens is that the light is getting more and more focused, and then it suddenly fans out because it has to be uncertain in some way. I don't know. That part gets weird and I don't quite understand it. But the uncertainty principle is one of these things that is strange and mysterious and interesting. And it's also cool because as a non-physicist, if you watch some videos and you read the Wikipedia pages, you can kind of get a little glimpse of what they're talking about. Obviously, we don't understand this with any subtlety, on the outside, but it's interesting to try to see the kind of problem that they're talking about, that physicists are working on, or this very weird aspect of the universe that we didn't know about, or were not able to adequately explain yet. So that's what Heisenberg did when he was 25. In 1929, he's now about 27 years old. He tours China, Japan, India, and the US, giving lectures, and in particular, he went to the University of Chicago. In 1932, he's now 31 years old, and he's awarded the Nobel Prize for Physics for his work up to that point. The following year, in 1933, when Hitler's party came to power in Germany, Heisenberg reportedly had some difficulty because of the German physics movement, which was opposed to theoretical physics in principle, apparently in part because they viewed it as Jewish physics or something, which that by itself sounds like a bad reason to dismiss a field. But it's worth noting that there are two physicists who were involved in the German physics movement who also got the Nobel Prize for Physics. One of them was Philipp Leonard, who got it in 1905, and Johannes Stark, who got it in 1919. Now, this seems like it was a bad call because theoretical physics apparently has all kinds of applications, and it is a big part of the overall picture of how we explain what we know about the universe today. But it was interesting to learn that there were some high-level capable physicists who were involved in it. But that happens in the history of science. Factions split off, and one of them turns out to be wrong. Heisenberg also enjoyed classical music and was an accomplished pianist, and he met his future wife, Elizabeth Schumacher, at a private recital in January of 1937. The two were married by April of that year, so 3 months later, and by January of the following year, Elizabeth gave birth to twins, a boy and a girl, and they had 5 more children over the next 12 years. And one of Heisenberg's sons, Jochen, is today Professor Emeritus of Physics at the University of New Hampshire. Heisenberg worked on the German nuclear program, which involved, to some unclear extent, a nuclear weapons program, which never really came to fruition, and it seems that Heisenberg didn't think that a weapon was possible. It's not clear. We'll look at that a little bit more in a minute. But he mostly worked on the potential for nuclear energy, it seems. And a guy named Moe Berg, who was an American baseball player who later worked as a spy for the Office of Strategic Services, the OSS, which was the predecessor to the CIA. And in December of 1944, Berg was assigned to attend a lecture by Heisenberg in Zurich and determine, quote, if anything Heisenberg said convinced him the Germans were close to a bomb, end quote. And if Berg thought that the Germans were close, he had orders to shoot Heisenberg. And Berg apparently went to the meeting and determined that the Germans were not close. It's generally accepted that by December of 1944, the Germans were not only not close to a bomb, they weren't even working on one. That by July of 1942 or so, they had scrapped the weapons program. In May of 1945, Heisenberg was captured by an Allied operation out of Urfeld and brought with a bunch of other German scientists to Farm Hall, which was a house near Cambridge in England that had been thoroughly bugged, and they were kept there for 6 months from July 1945 to January of 1946. And the primary goal of that program, of keeping them there, was to try to determine how close the Germans had been to building a nuclear weapon by listening to the conversations of these German scientists talking to each other. And the transcripts of these conversations are now called the Farm Hall transcripts, and you can buy books of them, and some of them are available online. I read them a little bit. They make for very interesting reading. Heisenberg says at one point, and remember, they're in a house with other German scientists speaking German. There's nobody else with them. They think that they're alone, but the house is bugged. He says, quote, I was absolutely convinced of the possibility of our making a uranium engine, but I never thought we would make a bomb. And at the bottom of my heart, I was really glad that it was to be an engine and not a bomb. I must admit that, end quote. So he thought that there could be a nuclear power source with this science, but he didn't think that there could be a bomb. And he was glad that there couldn't be a bomb. And in this next quote, there's a mention of somebody who's written in all caps, Segner, S-E-G-N-E-R. And there's a question mark on that in the transcript, which means they don't quite know who he's talking about. But Heisenberg says later, quote, about a year ago, I heard from Segner from the Foreign Office that the Americans had threatened to drop a uranium bomb on Dresden if we didn't surrender soon. At that time, I was asked whether I thought it possible, and with complete conviction, I replied, no, end quote. So they're in the second half of 1945 now. And he says about a year ago. So presumably in the second half of 1944 sometime, somebody in the German Foreign Ministry, according to Heisenberg, told him that the Americans had threatened to nuke Dresden if the Germans didn't surrender. And that person asked Heisenberg if he thought that was possible, and Heisenberg said he didn't think it was possible, meaning he didn't think that the Americans could have such a weapon. He didn't think that the weapon was possible. And I'd like to read all of the Farm Hall transcripts. That seems like a very interesting document. I just pulled a couple of these quotes from excerpts from them that I found online. After the war ended, Heisenberg had various jobs. He continued to do research for another 30 years, and Werner Karl Heisenberg died in Munich, in Bavaria, in what was at that time West Germany, in 1976. Now we can get into some passages from Physics and Philosophy by Heisenberg. And relatively early on, he talks about the use of what is more usually called a thought experiment, but he calls it an ideal experiment. Heisenberg writes, quote, "One frequently discussed what one called ideal experiments. Such experiments were designed to answer a very critical question irrespective of whether or not they could actually be carried out. Of course, it was important that it should be possible in principle to carry out the experiment, but the technique might be extremely complicated. These ideal experiments could be very useful in clarifying certain problems. If there was no agreement among the physicists about the result of such an ideal experiment, it was frequently possible to find a similar, but simpler experiment that could be carried out, so that the experimental answer contributed essentially to the clarification of quantum theory." End quote. So if they couldn't come to an agreement about how a given imaginary experiment would play out, they would instead develop an experiment around some adjacent idea and try to agree about how that one would play out. At one point when he's talking about detail, he says, quote, "Probability in mathematics or in statistical mechanics means a statement about our degree of knowledge of the actual situation. In throwing dice, we do not know the fine details of the motion of our hands, which determine the fall of the dice, and therefore we say that the probability for throwing a special number is just 1 in 6. End quote. And that thought caught my attention because probability has always seemed kind of weird to me. There's something strange about it. And we use probability and statistics to make decisions in our daily lives about where we want to live, what kind of food we want to eat, what we're going to do. We use it all the time, and for good reason. But there's still something strange about it. And what he's saying here is that when you roll a die, you say that the probability of getting a certain number is 1 in 6 because it's a 6-sided die. But we say that because we don't know all of the very detailed information about the die roll that you're going to do. You're going to hold the die in your hand, you're going to shake it a little, and you're going to throw it. And as you throw it, it's started with a certain number up. It's going to move across your fingers a certain number of times, and then it's going to spend a little bit of time in the air, and then it's going to hit the surface of the table, and it's going to roll a few more times, and it's going to land with a certain number facing up. And since we don't know how any of that is going to play out, we say that it's a 1 in 6 chance. But if we had precise enough information, very precise information about how many times it's going to rotate in your hand, how many times it's going to rotate in the air, exactly at what angle it's going to contact the table and with what force, and then how many times it's going to rotate after that. If we had all of that information, we could know that the chance of a certain number coming up is 100%. We could know what number is going to come up, and we could know that the chance that another number is going to come up is 0. So our explanation that there's a 1 in 6 chance of a certain thing happening is really only based on a lack of knowledge. Later, he's talking about the process of the development of what is now called the Copenhagen Interpretation. And in this passage, he mentions Bohr, and that's a reference to Niels Bohr, who won the Nobel Prize for Physics in 1922, and he and Heisenberg worked together a lot. Heisenberg writes, quote, "During the months following these discussions, an intensive study of all questions concerning the interpretation of quantum theory in Copenhagen finally led to a complete and, as many physicists believe, satisfactory clarification of the situation. But it was not a solution which one could easily accept. I remember discussions with Bohr which went through many hours till very late at night and ended almost in despair. And when at the end of the discussion I went alone for a walk in the neighboring park, I repeated to myself again and again the question, can nature possibly be as absurd as it seemed to us in these atomic experiments?" Skipping ahead, in this way, Since the spring of 1927, one has had a consistent interpretation of quantum theory, which is frequently called the Copenhagen Interpretation. This interpretation received its crucial test in the autumn of 1927 at the Solvay Conference in Brussels. Those experiments which had always led to the worst paradoxes were again and again discussed in all details, especially by Einstein. New ideal experiments were invented to trace any possible inconsistency of the theory, but the theory was shown to be consistent and seemed to fit the experiments as far as one could see." End quote. And as I've said, I'm not able to understand or explain any of this in any detail. It requires a lot of technical prerequisites. But we can have some fun trying to understand some of what Heisenberg is talking about. And the Copenhagen interpretation is one interpretation of quantum mechanics of perhaps a dozen or so. But it is apparently the oldest one, being developed, as Heisenberg says, around 1927, and it's among the most commonly taught. But there's also something called the many worlds interpretation, as well as a number of others, and he gives a chapter to explaining the Copenhagen interpretation. But it's not the kind of thing that's really easily summarized in a few sentences. And one of the things that Heisenberg talks about later in the book is how language is oriented around our experience of day-to-day life. And that, to a great extent, reflects what could be called classical mechanics. And the reason why it's difficult to explain quantum mechanics is because it doesn't act that way. It acts in a different way. And so in this chapter about the Copenhagen interpretation, one of the things that he talks about is something that he knows and that quantum physicists know makes him think the following about certain particles, which is that if you were to measure a particle in its position, and then you were to make some judgment about where it's going to go, and then you were to measure it again, and then see where it was. And so if this particle moved a little bit, it might make sense and it might be tempting to assume that in between the two measurements, you measured it at one time and it was in one position, and you measured it at another time and it was in another position, that in between those two measurements, the particle was somewhere in between those 2 points. Not necessarily that it moved in a straight line, but it was moving on some route in between those two. But for some reason, he opposes this idea. I don't want to explain what he's saying in the wrong way when I paraphrase it, so let me get a quote or two in here. Here's one. He writes, quote, "The momentum of light quantum of the gamma ray is much bigger than the original momentum of the electron if the wavelength of the gamma ray is much smaller than the size of the atom. Therefore, the first light quantum is sufficient to knock the electron out of the atom, and one can never observe more than one point in the orbit of the electron. Therefore, there is no orbit in the ordinary sense. The next observation, the third step, will show the electron on its path from the atom. Quite generally, there is no way of describing what happens between two consecutive observations. It is of course tempting to say that the electron must have been somewhere between the two observations, and that therefore the electron must have described some kind of path or orbit, even if it may be impossible to show which path. This would be a reasonable argument in classical physics, but in quantum theory, it would be a misuse of the language, which, as we will see later, cannot be justified. We can leave it open for the moment whether this warning is a statement about the way in which we should talk about atomic events or a statement about the events themselves, whether it refers to epistemology or to ontology. In any case, we have to be very cautious about the wording of any statement concerning the behavior of atomic particles." End quote. And one of the reasons I was more inclined to read this book about quantum theory rather than some other one is that the little bits of information that I hear about quantum theory are so strange, and as an outsider, I'm unable to verify what a writer is saying. But here we're looking at a text written by one of the guys who founded the field. And that doesn't mean that he's right about everything. It might turn out that the Copenhagen interpretation is not the best understanding of this, and there's another one that's more straightforward or something. But he put all this forward close to 100 years ago, and it's still one of the most taught interpretations. So this is a very serious scientist talking about this stuff. And so when he starts to say things that sound kind of spooky or fantastical, just really out there, even if it were a physicist, somebody who understands quantum theory, and they wrote a book and they said some of this stuff, I might say, well, you might be interpreting it in a weird way or something. I have no way to verify what you're talking about if this is some fringe belief or something. And you kind of go, it must be because it sounds so weird. But for me personally, I feel more that I can trust this. Not that it's the ultimate truth of the universe, but that it is a relatively current interpretation of the science, even though this book was published in 1962. We have this authoritative historical figure, Heisenberg, saying these wild things. Listen to this. Quote, "A real difficulty in the understanding of this interpretation arises, however, when one asks the famous question, but what happens really in an atomic event? It has been said before that the mechanism and the results of an observation can always be stated in terms of the classical concepts. But what one deduces from an observation is a probability function, a mathematical expression that combines statements about possibilities or tendencies with statements about our knowledge of facts. So we cannot completely objectify the result of an observation. We cannot describe what happens between this observation and the next. This looks as if we had introduced an element of subjectivism into the theory, as if we meant to say, what happens depends on our way of observing it, or on the fact that we observe it. Before discussing this problem of subjectivism, it is necessary to explain quite clearly why one would get into hopeless difficulties if one tried to describe what happens between two consecutive observations." End quote. And then he describes a thought experiment, which is sort of long and a little bit complicated, so I'm just going to jump to his conclusion. And he says, quote, "Now this is a very strange result, since it seems to indicate that the observation plays a decisive role in the event, and that the reality varies depending upon whether we observe it or not." End quote. And that's one of those weird, unexplained concepts that people then take and use it to try to justify all kinds of kooky things that it doesn't justify. But that's strange by itself, and Heisenberg is acknowledging how strange it is. Toward the end of that chapter, he writes, quote, "Our scientific work in physics consists in asking questions about nature in the language that we possess and trying to get an answer from experiment by the means that are at our disposal. In this way, quantum theory reminds us, as Bohr has put it, of the old wisdom that when searching for harmony in life, one must never forget that in the drama of existence we are ourselves both players and spectators. It is understandable that in our scientific relation to nature, our own activity becomes very important when we have to deal with parts of nature into which we can penetrate only by using the most elaborate tools." End quote. He then does a survey of a number of explanations by ancient Greek philosophers of matter and what the universe is made of. And one of the philosophers that he stops on is Heraclitus. And he says that if you switch out what Heraclitus says about fire for energy, then it's pretty much all consistent with modern physics. And he explains later exactly what he means by this comparison, not only with Heraclitus, but with the other philosophers that he talks about as well. But we'll get to that in a minute. He talks also about Anaxagoras, about Plato, and about Pythagoras and his followers. He writes, quote, "Here has been established the connection between religion and mathematics, which ever since has exerted the strongest influence on human thought. The Pythagoreans seem to have been the first to realize the creative force inherent in mathematical formulations. Their discovery that two strings sound in harmony if their lengths are in a simple ratio demonstrated how much mathematics can mean for the understanding of natural phenomena. For the Pythagoreans, it was not so much a question of understanding. For them, the simple mathematical ratio between the length of the strings created the harmony in sound. There was also much mysticism in the doctrines of the Pythagorean school, which for us is difficult to understand. But by making mathematics a part of their religion, they touched an essential point in the development of human thought." End quote. In this next passage, he's trying to describe what is an elementary particle. And as a layman, I appreciate him spending time on this kind of question, because one of the things that you hope that you would get from a field like particle physics is a way to think about what is very, very small. And whatever I've received secondhand from pop culture about this kind of physics has given me only a very vague sense of what is going on at that level. And I always thought that that was because I didn't understand it. And it is, but even the people who do understand it do not exactly know what's going on at that level, if knowing is to be demonstrated by a certain kind of explanation using everyday language. And what I mean is that they do know what's going on in terms of mathematical functions, but it's difficult to explain using the language that we usually use to communicate. It's easier to explain using this language of mathematics. But what's going on at that level, and remember, we're talking about the level of all matter, the behavior of the material that makes up you, that makes up where you're sitting, that makes up the building that you're in. We're talking about the behavior of matter at a very fundamental level. We're not talking about some planet in a distant galaxy. This is everything that you can see is best explained in this way at a certain level. And notice in particular in this next passage that what he says about elementary particles is that basic notions like shape and motion can't be applied to them consistently. But not only that, being, existence, can't be applied to them consistently. Heisenberg writes, quote, "Let us discuss the question, what is an elementary particle? We say, for instance, simply a neutron, but we can give no well-defined picture in what we mean by the word. We can use several pictures and describe it once as a particle, once as a wave, or as a wave packet. But we know that none of these descriptions is accurate. Certainly the neutron has no color, no smell, no taste. In this respect, it resembles the atom of Greek philosophy. But even the other qualities are taken from the elementary particle, at least to some extent. The concepts of geometry and kinematics, like shape or motion in space, cannot be applied to it consistently. If one wants to give an accurate description of the elementary particle, and here the emphasis is on the word accurate, the only thing which can be written down as description is a probability function. But then one sees that not even the quality of being, if that may be called a quality, belongs to what is described. It is a possibility for being or a tendency for being. Therefore, the elementary particle of modern physics is still far more abstract than the atom of the Greeks, and it is by this very property more consistent as a clue for explaining the behavior of matter." End quote. And wrapping up this comparison of Greek philosophy and modern physics, he writes, quote, "After this comparison of the modern views in atomic physics with Greek philosophy, we have to add a warning that this comparison should not be misunderstood. It may seem at first sight that the Greek philosophers have by some kind of ingenious intuition come to the same or very similar conclusions as we have in modern times only after several centuries of hard labor with experiments in mathematics. This interpretation of our comparison would, however, be a complete misunderstanding. There is an enormous difference between modern science and Greek philosophy, and that is just the empiristic attitude of modern science. Since the time of Galileo and Newton, modern science has been based upon a detailed study of nature and upon the postulate that only such statements should be made as have been verified or at least can be verified by experiment. The idea that one could single out some events from nature by an experiment in order to study the details and to find out what is the constant law in the continuous change did not occur to the Greek philosophers. Therefore, modern science has from its beginning stood upon a much more modest, but at the same time much firmer, basis than ancient philosophy. Therefore, the statements of modern physics are in some way meant much more seriously than the statements of Greek philosophy. When Plato says, for instance, that the smallest particles of fire are tetrahedrons, it is not quite easy to see what he really means. Is the form of the tetrahedron only symbolically attached to the element fire, or do the smallest particles of fire mechanically act as rigid tetrahedrons or as elastic tetrahedrons, and by what force could they be separated into the equilateral triangles, etc.? Modern science would finally always ask, how can one decide experimentally that the atoms of fire are tetrahedrons and not perhaps cubes? Therefore, when modern science states that the proton is a certain solution of a fundamental equation of matter, it means that we can from this solution deduce mathematically all possible properties of the proton and can check the correctness of the solution by experiments in every detail. This possibility of checking the correctness of a statement experimentally with very high precision and in any number of details gives an enormous weight to the statement that could not be attached to the statements of early Greek philosophy." End quote. And what he's talking about there is a very important point in the history of science and the history of thought. And it's this relationship between logic and empiricism or experimentation. That what the ancient Greeks were doing was working things through logically. It must be so because of this and therefore that, whatever. And by that, maybe they figured out some important things or at least asked some good questions. The trouble is, by only using that kind of inference, that kind of logical step-by-step walk, you can come to different conclusions, and all of the disputes between the ancient Greek philosophers demonstrate that. When different philosophers set out to answer a particular question using logic, they didn't all arrive at the same conclusion, or there was no mechanism by which they could be made to agree on a certain conclusion the way that experimental science really can force even an opponent to agree to an idea that they opposed initially. In that way, proper evidence with an experiment and it all being sorted out correctly is literally compelling. It compels you to accept it. And science took off, of course, when it went from using only logic, as was done in the classical time, to experimentation, starting with basically Galileo. We can talk about older examples, but Galileo is the very famous one that led to a lot of imitation after him, other people doing other experiments. And there's another problem that I think we've talked about on this podcast before, but Heisenberg doesn't mention it here. He kind of brushes on it, talking about the tetrahedron, but it's the problem of not being able to know which of your components are true or not. So if you have a lot of different Greek philosophers saying different things, and some of them are right, or verified 2,500 years later by a very advanced science, they had no way of knowing which ones were right. It might well have turned out that the opposite thing was right based on what they knew. And more importantly, even one philosopher who got one or two things right, or it was verified by this superior but imperfect means of verification that we call modern science, the same philosopher might have gotten other things wrong. So it's not even as if there was one philosopher who just spewed wisdom and got everything right all the way down the line. So then they still would have had no way of knowing which of these explanations is the best. Now, with all that being said, logic remains critical to modern science. It's just not sufficient. If you do an experiment or you present evidence for something, you need logic to then put that evidence in context, or to show that the experiment that you're doing is connected to this other claim that you're making. Otherwise, you could do an experiment and claim that it means anything. Then the experiment by itself is not relevant. We have to be able to put this experiment in a larger context, and we do that using logic. And I'm not cheerleading for Greek philosophy here or something. Modern science is the superior way of accessing what's true to the extent that we can know that about our environment. But I wouldn't want anyone to think that this was a motion from one approach to knowledge to another. It was an expansion of an approach to knowledge. That logic is not sufficient, but neither is experiment and empirical evidence. You need these two things together. And in this next passage, I felt vindicated by finding that Heisenberg agrees that Descartes is among the most important modern philosophers. And of course, nobody would deny that, but Heisenberg puts him in a very special position. And he even mentions, in particular, the discourse on method, at which we've looked on this podcast, and which I recommend you go and listen to if you haven't already. Heisenberg writes, quote, "The first great philosopher of this new period of science was René Descartes, who lived in the first half of the 17th century. Those of his ideas that are most important for the development of scientific thinking are contained in his discourse on method. On the basis of doubt and logical reasoning, he tries to find a completely new and, as he thinks, solid ground for a philosophical system. He does not accept revelation as such a basis, nor does he want to accept uncritically what is perceived by the senses. So he starts with his method of doubt. He casts his doubt upon that which our senses tell us about the results of our reasoning, and finally he arrives at his famous sentence, cogito ergo sum. I cannot doubt my existence since it follows from the fact that I am thinking. Skipping ahead, this basis of the philosophy of Descartes is radically different from that of the ancient Greek philosophers. Here the starting point is not a fundamental principle or substance, but the attempt of a fundamental knowledge. And Descartes realizes that what we know about our mind is more certain than what we know about the outer world." End quote. And later he expands a bit more on Descartes in his context and says it wasn't just Descartes setting a new direction, it was also a renewed interest in mathematics as a result of the Renaissance. And he points at the Reformation as developing this personal relationship with God, which gives a view of the individual and God together as distinct from the world. And this is a proto-scientific thought in his view. This is something that can set up the kind of thinking that would lead to experimentation, if you view yourself as very separate from the world, as a distinct thing. And then he wraps up by talking about how people also were maybe seeking a kind of knowledge that wouldn't be susceptible to sectarian wars that were common at that time. Heisenberg writes, quote, "Of course, it would be wrong to say that Descartes, through his new method in philosophy, has given a new direction to human thought. What he actually did was to formulate for the first time a trend in human thinking that could already be seen during the Renaissance in Italy and in the Reformation. There was the revival of interest in mathematics, which expressed an increasing influence of Platonic elements in philosophy, and the insistence on personal religion. The growing interest in mathematics favored a philosophical system that started from logical reasoning and tried by this method to arrive at some truth that was as certain as a mathematical conclusion. The insistence on personal religion separated the I and its relation to God from the world. The interest in the combination of empirical knowledge with mathematics as seen in the work of Galileo was perhaps partly due to the possibility of arriving in this way at some knowledge that could be kept apart completely from the theological disputes raised by the Reformation." End quote. And now here in this next section, he talks about how the Copenhagen interpretation and quantum theory generally conflict with this thing that he's calling the Cartesian partition, which was a foundational thought in modern science. That Descartes and his philosophy, as well as the confluence of historical trends that were going on at the time, led to this view of the individual examining the world. And there was this strict divide between those two things. And the Copenhagen interpretation, which apparently includes some element of the observer affecting the observed phenomenon, either blurs or erases this line between observer and observed, which had been so fundamental in science up to that point, and which is why Heisenberg suggests Einstein and others opposed it. Heisenberg writes, quote, "The situation changed to some extent through quantum theory, and therefore we now come to a comparison of Descartes' philosophical system with our present situation in modern physics. It has been pointed out before that in the Copenhagen interpretation of quantum theory, we can indeed proceed without mentioning ourselves as individuals, but we cannot disregard the fact that natural science is formed by men. Natural science does not simply describe and explain nature. It is a part of the interplay between nature and ourselves. It describes nature as exposed to our method of questioning. This was a possibility of which Descartes could not have thought, but it makes the sharp separation between the world and the I impossible. If one follows the great difficulty which even eminent scientists like Einstein had in understanding and accepting the Copenhagen interpretation of quantum theory, one can trace the roots of this difficulty to the Cartesian partition. This partition has penetrated deeply into the human mind during the 3 centuries following Descartes, and it will take a long time for it to be replaced by a really different attitude toward the problem of reality." End quote. Now this next one follows pretty closely after that first passage, but I wanted to stop and catch my breath because I had to read it a few times, but I can get it after I do that, and he uses a new word in an interesting way. He writes, quote, "The different forms of realism may be described as follows. We objectivate a statement if we claim that its content does not depend on the conditions under which it can be verified." End quote. So let's stop there. So he's talking about a kind of statement that we say is true independent of the situation that you use to verify the statement. It's true no matter what, no matter who's measuring, no matter where or how, whatever. It's always true. When we do that, we objectivate the statement. So presumably we would say the sky is blue, and we objectivate that statement because we say it's blue no matter what, except immediately we go, well, we see it as blue with our human eyes. Fine. Then let's go 2 + 2 is 4. Maybe that's a better one. We objectivate that statement because we say it is true no matter what circumstances you use to verify it. Notice we had to move from a sensual statement, a sense-based statement about a color, to a logical statement about math and quantity. So that's what he means by objectivate. Now let's keep going from there. Quote, "Practical realism assumes that there are statements that can be objectivated, and that in fact the largest part of our experience in daily life consists of such statements." End quote. So he's saying practical realism. He's describing a certain view, which is, I think, most of us operate under this view that most things can be objectivated. Their verification is independent of the circumstances under which they're verified. Most of us go around thinking that most of the things we think are true fit into that category. We objectivate most of our daily lives, and that view, he says, is practical realism. He's calling it that. He goes on, quote, "Dogmatic realism claims that there are no statements concerning the material world that cannot be objectivated." End quote. So that's a step further. Not just that some statements can be objectivated, but all of the statements about the material world, all the ones that are true, can be objectivated. Then he goes on, quote, "Practical realism has always been and will always be an essential part of natural science. Dogmatic realism, however, is, as we see it now, not a necessary condition for natural science. But it has in the past played a very important role in the development of science. Actually, the position of classical physics is that of dogmatic realism. It is only through quantum theory that we have learned that exact science is possible without the basis of dogmatic realism." End quote. So it sounds like what he's saying there is that quantum theory, or the Copenhagen interpretation of quantum theory, suggests that there are going to be statements about reality that are dependent on the circumstances in which they're verified. And winding up this chapter where he's talking about philosophy and modern physics, he summarizes some of what he's talked about up to that point, having to do with the limits of language in relation to physics and science, and ultimately to knowledge. And he talks about how we have these words and we use them in everyday contexts in a certain way, but we don't know how far their applicability goes because we've never gone out to the edges of their applicability. And certain kinds of science, particularly the physics that Heisenberg dealt with, operates beyond that edge. He writes, quote, "Modern physics has been used here as an example, or we may say as a model, to check the results of some important philosophic systems of the past, which of course were meant to hold in a much wider field. What we have learned, especially from the discussion of the philosophies of Descartes and Kant, may perhaps be stated in the following way. Any concepts or words which have been formed in the past through the interplay between the world and ourselves are not really sharply defined with respect to their meaning. That is to say, we do not know exactly how far they will help us in finding our way in the world. We often know that they can be applied to a wide range of inner or outer experience, but we practically never know precisely the limits of their applicability. This is true even of the simplest and most general concepts like existence and space and time. Therefore, it will never be possible by pure reason to arrive at some absolute truth. The concepts may, however, be sharply defined with regard to their connections. This is actually the fact when the concepts become a part of a system of axioms and definitions which can be expressed consistently by a mathematical scheme. Such a group of connected concepts may be applicable to a wide field of experience and will help us to find our way in this field, but the limits of the applicability will in general not be known, at least not completely. Even if we realize that the meaning of a concept is never defined with absolute precision, some concepts form an integral part of scientific methods since they represent for the time being the final result of the development of human thought in the past, even in a very remote past. They may even be inherited, and are in any case the indispensable tools for doing scientific work in our time." End quote. In a later section, he gives an interesting definition of past and future. He writes, quote, "When we use the term past, we comprise all those events which we could know at least in principle, about which we could have heard at least in principle. In a similar manner, we comprise by the term future all those events which we could influence at least in principle, which we could try to change and prevent at least in principle. It is not easy for a non-physicist to see why this definition of the terms past and future should be the most convenient one, but one can easily see that it corresponds very accurately to our common use of the terms." End quote. And he's right. When you hear that for the first time, it's not a terribly intuitive definition of the past and the future. That's not usually how we think about it. We imagine that we're moving along on this timeline, and there are certain things that are somehow behind us. That's the kind of language that we use. They have already happened. And then there are certain things that are in front of us. They haven't happened yet, and that's the past and the future. And he's saying that instead, the past is what you could in principle know or remember, and the future is what you could in principle influence. That the future is beyond our knowledge, it's unknowable, and the past is beyond our influence. It cannot be changed. And later he gives a detail about relativity that I thought was interesting, and that was basically that while there are two parts to relativity, one is special relativity and the other is general relativity. He says that he thinks that the evidence for special relativity, the initial theory in around 1905, is much stronger than the evidence for general relativity, which was developed sometime later. He writes, quote, "A careful analysis of this situation about 10 years later, in 1916, led Einstein to a very important extension of the theory of relativity, which is usually called the theory of general relativity. Before going into a description of the main ideas of this new theory, it may be useful to say a few words about the degree of certainty with which we can rely on the correctness of these two parts of the theory of relativity. The theory of 1905 and 1906 is based on a very great number of well-established facts, on the experiments of Michelson and Morley and many similar ones, on the equivalence of mass and energy in innumerable radioactive processes, on the dependence of the lifetime of radioactive bodies on their velocity, etc. Therefore, this theory belongs to the firm foundations of modern physics and cannot be disputed in our present situation. For the theory of general relativity, the experimental evidence is much less convincing, since the experimental material is very scarce. There are only a few astronomical observations which allow a checking of the correctness of the assumptions. Therefore, this whole theory is more hypothetical than the first one." End quote. And in a later chapter, he answers some of the people who have argued against the Copenhagen interpretation. And among them are two physicists who opposed it, essentially on the grounds that the Copenhagen interpretation opposes dialectical materialism. That is a section of Marxist theory. And Heisenberg quotes from their article and answers it, and then he makes a general comment about science and ideology. He writes, quote, "We cannot possibly expect those thinkers who a century ago introduced dialectic materialism to have foreseen the development of quantum theory. Their concepts of matter and reality could not possibly be adapted to the results of the refined experimental technique of our days. Perhaps one should add at this point some general remarks about the attitude of the scientist to a special creed. It may be a religious or a political creed. The fundamental difference between the religious and the political creed, that the latter refers to the immediate material reality of the world around us, while the former has as its object another reality beyond the material world, is not important for this special question. It is the problem of creed itself that is to be discussed. From what has been said, one would be inclined to demand that the scientist should never rely on special doctrines, never confine his method of thinking to a special philosophy. He should always be prepared to have the foundations of his knowledge changed by new experience. But this demand would again be an oversimplification of our situation in life for two reasons. The first is that the structure of our thinking is determined in our youth by ideas which we meet at that time or by getting into contact with strong personalities from whom we learn. This structure will form an integrating part of all our later work, and it may well make it difficult for us to adapt ourselves to entirely different ideas later on. The second reason is that we belong to a community or a society. This community is kept together by common ideas, by a common scale of ethical values, or by a common language in which one speaks about the general problems of life. The common ideas may be supported by the authority of a church, a party, or the state. And even if this is not the case, it may be difficult to go away from the common ideas without getting into conflict with the community. Yet the results of scientific thinking may contradict some of the common ideas. Certainly, it would be unwise to demand that the scientist should generally not be a loyal member of his community, that he should be deprived of the happiness that may come from belonging to a community, and it would be equally unwise to desire that the common ideas of society, which from the scientific point of view are always simplifications, should change instantaneously with the progress of scientific knowledge, that they should be as variable as scientific theories must necessarily be. And skipping ahead, the scientist's first claim will always be intellectual honesty, while the community will frequently ask of the scientist that, in view of the variability of science, he at least wait a few decades before expressing in public his dissenting opinions. There is probably no simple solution to this problem if tolerance alone is not sufficient, but some consolation may come from the fact that it is certainly an old problem belonging to human life." End quote. And in that passage, he talks about this problem we're all familiar with. It is that there's the opinion of the community, or the time that the scientist is living in, and he may encounter something that contradicts that. And Heisenberg is talking about this in the context of these two guys who were apparently Marxists themselves, or at least opposed his ideas partially or entirely on Marxist grounds. And so he's talking about the need for the scientist to be detached from ideology. But he acknowledges this human side of it, which is more than you often hear when people bring this topic up, which is, he says, the scientist is also a part of the community, and he has his upbringing and his beliefs, and it would be too much to ask for him to not participate in the community. And interestingly, he also says you wouldn't want the beliefs of the community to be a one-to-one correlation with current scientific beliefs, which change very quickly and are often symbolic or simplified. And he also says, quote, "If in our time political doctrines and social activities take the part of positive religion in some countries, the problem is still essentially the same," end quote. That science might go against political doctrine or social activities, but that's not different from it contradicting an established religion. And he doesn't have a good answer to all this, but he points it out, and I thought it was interesting that this historically significant scientist gave more room than you usually hear for both the scientist and his need for community and for the community generally, while he's talking about this standard of dispassionate analysis that's the basis of what it is to be a scientist. Again, later he comes back to this point about the difficulty of explaining what's going on at the quantum level. And this passage helped me to understand why I can't even understand intuitively what's going on when people talk about quantum physics. Even if you sit and watch a documentary about it, you don't come out of it with a simple model in your mind about more or less what's going on or something. And the reason is because, as we've touched on already, language relates to everyday life, which in the physics context relates to classical physics. And in atomic physics, classical physics doesn't apply, or it doesn't apply in the same way. And in parallel, the language that we use to describe our daily lives does not apply in the same way. Heisenberg writes, quote, "Every description of phenomena, of experiments and their results, rests upon language as the only means of communication. The words of this language represent the concepts of daily life, which in the scientific language of physics may be refined to the concepts of classical physics. These concepts are the only tools for unambiguous communication about events, about the setting up of experiments, and about their results. If, therefore, the atomic physicist is asked to give a description of what really happens in his experiments, the words description and really and happens can only refer to the concepts of daily life or of classical physics. As soon as the physicist gave up this basis, he would lose the means of unambiguous communication and could not continue in his science. Therefore, any statement about what has actually happened is a statement in terms of the classical concepts and, because of thermodynamics and of the uncertainty relations, by its very nature incomplete with respect to the details of the atomic events involved. The demand to describe what happens in the quantum theoretical process between two successive observations is a contradiction in ejecto, since the word describe refers to the use of the classical concepts. While these concepts cannot be applied in the space between the observations, they can only be applied at the points of observation." End quote. And we can wrap up by looking at two reflections from Heisenberg on the impact of physics specifically and science and technology broadly on our view of the world and on human life in the 20th and now the 21st century. He writes, quote, "Coming back now to the contributions of modern physics, one may say that the most important change brought about by its results consists in the dissolution of this rigid frame of concepts of the 19th century. Of course, many attempts had been made before to get away from this rigid frame, which seemed obviously too narrow for an understanding of the essential parts of reality. But it had not been possible to see what could be wrong with the fundamental concepts like matter, space, time, and causality that had been so extremely successful in the history of science. Only experimental research itself, carried out with all the refined equipment that technical science could offer, and its mathematical interpretation, provided the basis for a critical analysis, or one may say enforced the critical analysis of these concepts, and finally resulted in the dissolution of the rigid frame. This dissolution took place in two distinct stages. The first was the discovery, through the theory of relativity, that even such fundamental concepts as space and time could be changed, and in fact must be changed on account of new experience. This change did not concern the somewhat vague concepts of space and time in natural language, but it did concern their precise formulation in the scientific language of Newtonian mechanics, which had erroneously been accepted as final. The second stage was the discussion of the concept of matter enforced by the experimental results concerning the atomic structure. The idea of the reality of matter had probably been the strongest part in the rigid frame of concepts of the 19th century, and this idea had at least to be modified in connection with the new experience. End quote. And then a bit later, in a slightly different context, he says, quote, "Of course, such remarks should not be misunderstood as an underestimation of the damage that may be done or has been done to old cultural traditions by the impact of technological progress. But since this whole development has for a long time passed far beyond any control by human forces, We have to accept it as one of the most essential features of our time and must try to connect it as much as possible with the human values that have been the aim of the older cultural and religious traditions." End quote. And those were some of the passages that I wanted to show you from Physics and Philosophy, The Revolution in Modern Science by Werner Heisenberg. If you hadn't had enough, I encourage you to go and get this book and read it. It's not very long. It's surprisingly readable given the subject matter, and it has all kinds of interesting stuff that I didn't have time to get to. If you enjoyed this podcast, I hope you will send it to a thoughtful friend who you think will enjoy it as well, and go over to my website, volrathpublishing.com, and pick up a copy of the edition of Mary Shelley's Frankenstein that I've printed. I have it at a good price with free shipping, original cover art, excellent print quality, 97 footnotes throughout the book. Mary Shelley's Frankenstein is generally taken as the origin of the entire genre of science fiction. It is more relevant today than it was when it was first published over 200 years ago. It has a lot to think about, a lot to talk about. If you haven't read it, you should absolutely order yourself a copy now and do so. If you have read it, but you don't own a copy, you should have a copy on your shelf. You should get my edition. And if you have read it and you own a copy, you should still order a copy to get it for a friend or a family member. It makes an excellent gift. This is a good book, both for somebody who is a seasoned reader of classic literature, as well as for somebody who maybe is not as used to reading old books, but is interested in getting into it. One of my goals in preparing this edition was to make something that I would be glad to have on my bookshelf, and I'm pleased to say that I was able to accomplish that. The edition of Frankenstein in my library is the one that I printed, and I'm sure that this will make an excellent addition to your library as well. So I hope you'll go over there right now and get yourself a copy. Farewell until next time. Take care, and happy reading.